We are Photo-Electron Soul, launching a new era of e-beam technology with semiconductor photocathodes. In this video, we will show you how our laser-driven e-beam unlocks advanced inspection and metrology capabilities that were previously impossible. Let's dive in. To understand the need for change, let's look at the current state of electron sources. For nearly 50 years, the fundamental principles of emission have remained unchanged. While semiconductors advance, thermal cathodes and field emitters are approaching their physical limits. We are challenging these old principles, bringing innovation to e-beam technology for the first time in half a century. So, how does our approach differ? Traditional thermal and field emitters rely on heat or electric fields, where emission current changes non-linearly. This makes precise control difficult. In contrast, our photocathode uses a laser to emit electrons in direct proportion to its intensity. This linear relationship enables much more precise control than ever before. With a photocathode, we can precisely control the probe current simply by adjusting the laser intensity. Crucially, this is achieved without changing the beam geometry. We use a cesium-coated gallium nitride semiconductor photocathode, driven by a visible blue laser. This laser-driven approach enables versatile beam generation, such as pulsed and multi-beam operation. In particular, our system can generate nanosecond pulsed electron beams, with rise and fall times of about 1.5 nanoseconds and peak currents up to 1 milliampere. Now let's take a look at the actual hardware that makes this possible. The photo on the left shows our electron gun product. The gallium nitride photocathode is installed inside an ultra-high vacuum chamber. The excitation laser is introduced from the atmosphere side, allowing for flexible intensity and pulse modulation outside the vacuum environment. We have demonstrated industrial-grade continuous e-beam operation with an uptime ratio of 96% and a current stability better than 0.05% RMS. Downtime is mainly due to periodic cesium recoating of the photocathode surface, which is well managed. This system is now ready for integration into inspection and metrology equipment. We know that changing a core technology, like the electron source, is a significant step involving real risks. That's why our approach is focused. We provide our photocathode electron gun as a high-value core component. We are committed to delivering technological value that traditional beam technologies simply cannot match. Our goal is to empower partners by unlocking capabilities far beyond the limits of traditional technology. Now let's see how we've integrated our technology into actual systems. Since electron beam metrology and inspection is fundamentally based on SEM, we replaced only the electron gun in a conventional SEM to create a photocathode SEM. This allows us to explore new applications. Importantly, our electron gun can also be retrofitted into existing SEM systems. Now, let's look at the unique value only a photocathode can provide. The first is digital selective e-beaming, or DSEB. This technology changes the way we use the electron beam itself. In a standard SEM, a focused beam scans across the wafer to generate a secondary electron image. DSEB takes this step further by synchronizing that scanning motion with the pulsed beam structure from the photocathode. This enables pixel-by-pixel control of a radiation dose within the SEM image. Here is the DSEB operation. You can see the photocathode SEM interface on the left and resulting image on the right. By drawing an arbitrary shape and setting intensity in the photocathode SEM interface, and simply double-clicking, the defined region is selectively irradiated in the field of view. You can even overlay arbitrary images and irradiate according to image contrast. So, what kind of inspection value does DSEB actually provide? One important application is the non-contact electrical operation of MOSFETs. While conventional voltage contrast imaging allows observation of static charge distributions, it does not provide active control of device operation. With DSEB, we can selectively modulate electron irradiation at specific regions, enabling dynamic electrical state manipulation during SEM imaging. To verify this concept, we examined MOSFETs inside a 3D NAND memory device. Under low landing energy conditions, the floating gate accumulates positive charge and appears dark. In contrast, the source plug is grounded and appears brighter than the gate. The drain plug becomes conductive due to channel formation induced by the positively charged gate. As a result, it is electrically connected to the source and also appears bright. Now let us examine what happens when we selectively turn off electron irradiation only to the gate region using DSEB. As shown in the video, when irradiation to the gate is locally suppressed, the drain region becomes dark. This occurs because the positive charging of the gate is reduced, the channel disappears, and the drain becomes electrically floating. In other words, DSEB enables in-situ switching of a MOS transistor inside a real device, directly observed through SEM imaging. We have successfully demonstrated this in-situ switching for both N-type and P-type MOS transistors, proving the versatility of the DSEB method. Furthermore, we took this step further. By varying the gate irradiation current and monitoring the drain contrast, we were able to extract the threshold voltage, or VTH. This shows that quantitative electrical evaluation is possible using electron beam control alone, without electrical contacts. Another critical application for DSEB is charge suppression. In standard SEM imaging, localized charge accumulation causes image distortion, noise, and even sample damage, especially in heterogeneous structures. To address these challenges, we have applied a method of intermittent irradiation using DSEB. In conventional SEM, the entire field is irradiated continuously. With our intermittent irradiation approach, we irradiate only a fraction of pixels in each frame. For example, just 1 out of 5 pixels. The irradiated pixel shifts with each subsequent frame, and we integrate to reconstruct the full image. This technique reduces local charge buildup while maintaining image quality. Let's look at a practical example. This sample shows a hole in a silicon substrate created by laser processing. Notice the debris, likely amorphous silicon or oxide, remains near the hole edges and bottom. These specific regions are prone to charging. In this demonstration, intermittent irradiation was applied, where only 1 in 20 pixels received the beam. On the left, you can see the moving stripe pattern in each frame. On the right, our software integrates frames 1 through 20 to reconstruct the full image. Now, pay close attention. When the stripe scanning is stopped, you see darkening and tailing artifacts. This is a direct result of charge accumulation. However, when intermittent irradiation resumes, these effects are mitigated. This proves that our photocathode can achieve nanosecond-scale pulsing during horizontal scans, effectively suppressing charge-up. Beyond simple stripe patterns, our technology supports a wide variety of irradiation schemes, such as block or dot patterns. This flexibility is key, as it allows us to optimize the beam delivery depending on both the specific material and structure of the sample, as well as its unique charging behavior. We have already evaluated various irradiation patterns and their effects on imaging. Now, let's take another leap forward. Building on the DSEB concept, we've developed yield-controlled e-beaming, or YSEB. This enables high-precision control of secondary electron yield on a pixel-by-pixel basis. We move beyond where electrons are irradiated to controlling how much signal is generated at every pixel. Let's look at the principle behind this. In conventional SEM imaging, a constant probe current is scanned across the field of view. The resulting secondary electron intensity varies depending on material properties and surface geometry, and this variation forms the image contrast. In YSEB, we fundamentally invert this relationship. Using pixel-by-pixel feedback, such as PID control, we dynamically adjust the probe current so that the secondary electron intensity remains constant across the entire image. In other words, we are no longer visualizing secondary electron intensity. We visualize the specific probe current required to maintain a constant yield. As a result, the conventional secondary electron contrast disappears, and a new type of contrast emerges in the probe current distribution. The brightness-inverted probe current map is defined as the YSEB image. Next, let's look at a practical application of YSEB imaging, specifically for deep trenches and TSV structures. We will show you how this method overcomes the imaging challenges typically found in these high aspect ratio features. In SEM observation of high aspect ratio trenches and TSVs, we face major structural challenges. First, in deep holes, the incident electrons strike the sidewalls at shallow angles. This enhances secondary electron emission from sidewalls, and especially from edges. On the other hand, secondary electrons generated at the bottom of deep holes have a limited solid angle through which they can escape to the detector. As a result, detection efficiency at the bottom is significantly lower than at the surface. Because regions with very different emission and detection efficiencies coexist within the same field of view, it becomes extremely difficult to optimize contrast in conventional SEM. This is exactly where YSEB demonstrates strong advantage, effectively managing these extreme yield differences. Let's see YSEB action. This video shows a silicon trench with a width of 1 micrometer and a depth of 30 micrometers, an aspect ratio of 30. As YSEB control is activated, you can see the irradiation intensity being adjusted in according to the local secondary electron yield. Regions with strong emission, like the edges and upper sidewalls, are irradiated less. Conversely, regions with weak emission, such as the bottom of the trench, are irradiated more. Eventually, the conventional SEM image becomes uniform in intensity, while the YSEB image reveals clear structural details inside the trench, including particle shapes at the bottom. Furthermore, we now present a comparison of imaging for TSVs with a width of 5 microns and a depth of 50 microns. In this slide, the bottom row shows a depth of 50 microns, The middle row consists of shallower holes filled with NaCl crystals. On the left, we have the conventional SEM image, and on the right, the YSEB image. By looking at these intensity 3D maps, the difference becomes striking. In these results, you can see that edge-related secondary electron amplification is significantly suppressed in YSEB imaging. Furthermore, look closely at the bottom signals. The difference in bottom signal between the fully deep TSV and the partially filled TSV is more clearly distinguished in YSEB than in conventional SEM. This indicates that YSEB enhances sensitivity to variations in bottom structure and depth. In summary, with the emergence of gallium nitride semiconductor materials, laser-driven electron beam technology based on semiconductor photocathodes has finally reached a level suitable for industrial application. Regarding the applications of DSEB and YSEB, with DSEB, we demonstrated non-contact operation of MOS transistors by selectively switching gate irradiation on and off, and intermittent irradiation with DSEB showed strong potential for suppressing charge-up effects. Additionally, with YSEB, we demonstrated improved observation of the bottoms of deep holes with aspect ratios greater than 10. Importantly, all of these new applications were realized simply by replacing the electron beam source. No modifications were required for the SEM column, detectors, or stages, ensuring a straightforward integration into existing systems. Finally, we would like to express our deepest gratitude. Some of the developments featured in this video were made possible through our collaboration with Mr. Yasuda, Professor Honda, Professor Amano. We sincerely thank our collaborators for their invaluable support and expertise, which were essential to the success of this project. Thank you.